welcome to this problem walkthrough. Today, we'll be solving LeetCode problem number 80, remove duplicates from sorted array 2. This is a fascinating problem that deals with modifying arrays in place while adhering to specific constraints. Let's dive in and explore the solution approaches together. Here, the problem asks us to work with an array nums that is already sorted in non-decreasing order. The goal is to modify this array in place so that each unique element appears at most twice, while maintaining the relative order of the elements. After performing these modifications, we need to return the new length of the array, denoted by k. Importantly, the first k elements of the array should contain the final valid result, and anything beyond this range is irrelevant. For input, we are given the array nums, and the output consists of the integer k, along with the modified version of nums, where only the first k elements are relevant. To understand this better, let's look at an example. Suppose the input array is nums equals 1, 1, 1, 2, 2, 3. For the output, we get k equals 5 and nums equals 1, 1, 2, 2, 3. Here's how this result is derived. The number 1 appears 3 times in the array, but since each unique element can appear at most twice, only the first 2 occurrences of 1 are retained. The number 2 appears twice, which is within the allowed limit, so both instances remain. Finally, the number 3 appears once, which is also valid. As a result, the modified array is 1, 1, 2, 2, 3, with a new length of k equals 5. Another example helps further clarify the problem. If nums equals 0, 0, 1, 1, 1, 1, 2, 3, 3, the output becomes k equals 7 and nums equals 0, 0, 1, 1, 2, 3, 3. Here's why: the number 0 appears twice, so both instances are kept. The number 1 appears 4 times, but only the first 2 are allowed to remain. The number 2 appears once, which is valid, and the number 3 appears twice, so both instances are retained. This results in the modified array 0, 0, 1, 1, 2, 3, 3, with a new length of k equals 7. Now consider a simpler case where the input is nums equals 1, 1, 1, 1. The output is k equals 2 and nums equals 1, 1. Here, the number 1 appears 4 times, but since only the first 2 instances are allowed, the modified array contains just 1, 1. The new length, k, is 2. To summarize, the constraints ensure that at most 2 instances of any unique number are retained, regardless of how many times it originally appears in the array. It is also important to note a few constraints and edge cases. First, the array nums is guaranteed to be sorted, which simplifies the process of identifying duplicates. Elements beyond the first k indices are irrelevant and can be ignored. Additionally, the solution must be implemented in place, meaning no extra space can be used to store a copy of the array. For edge cases, if nums contains only one element, the array is already valid. Similarly, if all elements are unique, the array remains unchanged. Finally, for large inputs, such as when nums.length is 10,000, the solution must be efficient. By adhering to these rules, we can ensure that the modified array satisfies the problem's requirements. To start with, let's consider the brute force approach to solving this problem. The intuition here is fairly straightforward. We iterate through the array, count the occurrences of each element, and then construct a new array that ensures no element appears more than twice. Once this new array is formed, we copy its contents back into the original array. The procedure involves looping through the array to count occurrences, appending elements to a temporary array only if their count is less than or equal to 2. And finally copying the temporary array back into the original. However, this method has significant drawbacks. The time complexity is O(n squared), which arises from the inefficiency of inserting elements and copying parts of the array. Additionally, the space complexity is O(n), because we rely on a separate array to store intermediate results. Most importantly, this approach fails to meet the in-place requirement specified in the problem, making it less desirable as a solution. Now, to address the inefficiencies of the brute force method, we turn to the two-pointer technique, which offers a more optimized solution. The key intuition behind this method is to use 2 pointers, one pointer, called insert_POS, to track the position where the next valid element should be inserted, and another pointer, I, to traverse the array. Since the array is sorted, any duplicates will appear consecutively, simplifying the process of counting occurrences. To ensure that no element appears more than twice, we can compare the current element at nums I with the element at nums insert underscore POS 2. If the current element can be added either because we're filling one of the first two positions or because it doesn't match the element 2 steps back, we assign it to the insert underscore POS position and then increment insert underscore POS. By the end of this traversal, the first insert underscore POS elements of the array will form the modified result, satisfying the problem's constraints. Analyzing the two-pointer technique, we see that its time complexity is O(n), as we traverse the array just once. The space complexity is O(1), since all modifications are done in place without requiring any additional memory. These efficiencies make the approach highly advantageous. Not only does it meet the problem's in-place requirement, but it is also simple to implement, avoiding the overhead associated with creating temporary arrays. The technique effectively balances performance and practicality, ensuring the solution is optimized for both time and space. Ultimately, we selected the two-pointer technique as our final strategy because it is the most optimal solution in terms of time and space complexity. By leveraging the sorted nature of the array, this method allows us to efficiently track and limit duplicates, all while modifying the array in place. One key insight that made this approach work was realizing that we only need to check the last two inserted elements, specifically the one at nums, insert underscore POS 2. This insight eliminated the need for nested operations or additional structures, which were drawbacks of the brute force approach. While the two-pointer method does require careful management of indices and conditions, this level of complexity is minor compared to the inefficiencies of the alternative. In conclusion, this method strikes the perfect balance between simplicity, efficiency, and adherence to the problem's constraints, making it the ideal solution. In this problem, our goal is to modify a sorted array so that each unique element appears at most twice, while preserving the order of the elements. After the modification, the array should not contain any extra elements past the final valid length. To achieve this, we start by initializing two pointers, write underscore index and read underscore index. The write underscore index keeps track of the position where the next valid element should be written, while read underscore index is used to traverse the array. Both pointers are initially set to 0. This setup allows us to efficiently process the array in a single pass while making the necessary modifications in place. Now, as we traverse the array using the read underscore index, we maintain a variable called count to track the number of consecutive appearances of the current element. If the current element is the first one we're encountering or is different from the previous element, we reset count to 1. Otherwise, we increment count since the same element is repeated. For each element, we check the value of count. If it is less than or equal to 2, we write the current element at the position indicated by write underscore index and move the write underscore index forward. This ensures that only up to 2 occurrences of each element are retained in the array. Once the traversal is complete, the array is modified in place up to the position specified by write underscore index, and any elements beyond that point can be ignored. Let's walk through an example to see how the algorithm works. For the input array nums equals 1, 1, 1, 2, 2, 3, we start by initializing write underscore index to 0, read underscore index to 0, and count to 1. During the first iteration, the current element is 1. Since it's the first element, we set count to 1, write 1 at nums, write underscore index, and increment write underscore index to 1. In the second iteration, the current element is still 1, so we increment count to 2, write 1 again at nums, write underscore index, and move write underscore index to 2. These steps ensure that the first 2 occurrences of 1 are retained. In the third iteration, the current element is 1 again, so we increment count to 3. Since count exceeds 2, we skip writing this element, effectively removing the third occurrence of 1. Next, in the fourth iteration, the current element is 2, which is different from the previous one. We reset count to 1, write 2 at nums, write underscore index, and increment write underscore index to 3. In the fifth iteration, the current element is 2 again, so we increment count to 2, write 2 at nums, write underscore index, and move write underscore index to 4. This ensures that only 2 occurrences of 2 are retained. In the sixth iteration, the current element is 3, which is a new element. We reset count to 1, write 3 at nums, write underscore index, and increment write underscore index to 5. At this point, we have processed the entire array, and the modified array is 1, 1, 2, 2, 3. Key insights from this approach include the in-place modification of the array, which is made possible by the right_index pointer. The use of two pointers allows the algorithm to run in O(n) time complexity, as each element is processed exactly once. Additionally, it handles edge cases such as empty arrays, arrays with all unique elements, or arrays where all elements are the same, ensuring correctness in all scenarios. From a data structures perspective, this algorithm efficiently reuses the input array for both reading and writing, ensuring in-place modification. The only additional variable needed is the count, which tracks the number of consecutive appearances of the current element. In terms of complexity, the time complexity is O(n), where n is the length of the array, since we make a single pass through the array. The space complexity is O(1), as no additional data structures are used. This makes the solution highly efficient and suitable for large input sizes. The solution focuses on modifying the input array nums in place to enforce the constraint that each unique element appears at most twice. Here's a detailed breakdown of the implementation. 1. Initialization. A pointer right_index is initialized to 0. This pointer determines the position in the array where the next valid element will be written. 2. Iterating through the array. The code iterates through each element number in the array nums. 3. Validation logic. The condition right_index2 or number nums right_index2 ensures that if right_index is less than 2, we accept the element directly because the first two elements of any sequence are always valid. If right_index is 2 or more, we check if the current element number is greater than the element 2 positions back, nums right_index2. This ensures no more than 2 duplicates for any value. For updating the array, if the condition is satisfied, the current element number is written to the position right_index, and right_index is increment. 5. Returning the result. After processing all elements, right_index represents the length of the modified array, which is returned as the result. This approach works in O(n) time complexity, as we traverse the array once, and it uses O(1) space since no additional data structures are used. The solution efficiently handles edge cases, such as arrays with fewer than 2 elements or arrays with all identical elements. This Java implementation mirrors the logic of the Python solution for LeetCode problem number 80, remove duplicates from sorted array 2. It uses a single pass to maintain a pointer for the position to overwrite valid elements in the array, ensuring that each element appears at most twice. Key differences include explicit type declarations, enhanced for loops, and Java's array handling. To start, we're given the input array 1, 1, 1, 2, 2, 3. The goal is to modify this array in place so that each element appears at most twice. We also need to return the new length of the modified array. Initially, the right_index is set to 0, which represents the position where the next valid element will be written. In the first iteration, we look at the number 1. Since right_index is less than 2, we allow this number and write it at position 0. We then increment right_index to 1. In the second iteration, we encounter another 1. Again, because right_index is still less than 2, we keep it, write it at position 1, and increment right_index to 2. At this point, the array remains unchanged, but right_index has moved to 2, indicating that the next valid element will be placed at position 2. In the third iteration, we encounter another 1. This time, we check if this one should be kept. Since it is equal to the value at nums right_index 2, which is also 1, we skip this element because it would exceed the limit of 2 occurrences. The right_index remains at 2. Next, we process the number 2 in the fourth iteration. Here, 2 is greater than nums right_index 2, which is 1, so it can be included. We write 2 at position 2 and increment right_index to 3. In the fifth iteration, we encounter another 2. Since 2 is still greater than nums right_index 2, which is 1, we keep it and write it at position 3. The right_index moves to 4. Finally, in the sixth iteration, we process 3. Since 3 is greater than nums right_index 2, which is 2, we include it, write it at position 4, and increment right_index to 5. At the end of these steps, the array is 1, 1, 2, 2, 3, 3, and right underscore index is 5. With the execution complete, we see that the modified array is 1, 1, 2, 2, 3, and the return value is 5, representing the length of the modified array. Now, let's look at another example. This time, the input array is 0, 0, 1, 1, 1, 1, 2, 3, 3. Again, we initialize the right underscore index to 0, and will process each element while adhering to the rule of allowing at most 2 occurrences of any number. In this example, during the first and second iterations, we encounter 0 twice. Since right underscore index is less than 2, both 0s are kept, and right underscore index is updated to 2. Moving on, the third and fourth iterations involve the number 1. Here, since 1 is greater than nums, right underscore index 2, both times, we keep the first two 1s, and right underscore index becomes 4. In the fifth and sixth iterations, we encounter 2 more 1s, but these are skipped because they are equal to nums, right underscore index 2. The right underscore index remains at 4. In the seventh iteration, the number 2 is processed. Since 2 is greater than nums, right underscore index 2, we included an increment right underscore index to 5. Finally, in the 8th and 9th iterations, we process 3 twice. Since 3 is greater than nums, right underscore index 2, in both cases, we include both, and right underscore index is updated to 7. By the end, the modified array is 0, 0, 1, 1, 2, 3, 3, and right underscore index is 7. In this second example, the final output is the array 0, 0, 1, 1, 2, 3, 3, and the return value is 7. Lastly, consider a simpler case where the input is 1, 1, 1, 1, 1. Here, we only keep the first two 1s because all subsequent 1s exceed the allowed limit of 2 occurrences. The final state of the array is 1, 1, and the return value is 2. This demonstrates how the solution effectively handles duplicates by adhering to the condition of keeping at most 2 occurrences of each number. The time complexity of the solution is O(n), where n is the length of the input array nums. This is because the algorithm processes each element in the array exactly once using a single for loop. In each iteration, it performs a constant time comparison with the condition right underscore index 2 or number nums, right underscore index 2. If the condition is true, it updates the value at nums, right underscore index, and increments the right underscore index pointer. These operations, being O(1), do not add any extra overhead. So, the overall time complexity is determined by the number of elements in the array, which makes it linear, or O(n). The space complexity of the solution is O(1). This is because the algorithm modifies the input array nums in place, meaning it does not use any additional data structures to store results. Instead, it relies on the right underscore index pointer to manage the array modifications. The only extra space required is for a few variables, such as right underscore index, which is a single integer and thus takes constant space. Since no memory usage scales with the size of the array, the space complexity remains O(1). Additionally, whether the input contains no duplicates, some duplicates, or all duplicates, the loop always iterates once through the array, maintaining a consistent O(n) time complexity across best, average, and worst cases. When comparing this approach to a naive solution, the differences are clear. A naive method might involve creating a new array to store valid elements, followed by copying it back to nums. This would require O(n) time for traversal and O(n) space for the additional array. In contrast, the optimized approach modifies the array in place, eliminating the need for extra memory while still achieving O(n) time complexity. From a mathematical perspective, the big O analysis is straightforward. The algorithm performs exactly n iterations, processing each element once, with constant time operations during each iteration. This ensures the time complexity is O(n). Additionally, since the space usage is constant and does not depend on the input size, the space complexity remains O(1). This balance of minimal runtime and memory usage makes the solution optimal for this problem. When solving this problem, there are several common mistakes that you should be mindful of. One frequent error is misunderstanding the constraints. For example, not properly accounting for edge cases such as an empty array, an array with only one element, or an array where all elements are identical. These situations can cause runtime errors or produce incorrect results. To address this, make sure to test your solution with these edge cases and clarify constraints during interviews. Another mistake involves modifying the input array incorrectly. Developers sometimes overwrite elements too early or fail to shift elements properly, which results in lost data. A good way to avoid this is by using the two-pointer technique or carefully tracking indices during in-place modifications. Overcomplicating the solution is another pitfall. Using nested loops or unnecessary data structures can increase both time and space complexity. Instead, aim for simplicity by focusing on efficient techniques. Lastly, neglecting time complexity can be an issue. For example, using a brute force approach with nested loops results in O(n)² complexity, even though this problem can be solved in linear time. Always analyze your solution's time complexity and strive for the most optimal approach. Skipping validation of the output is another mistake to watch out for. For instance, it's important to double-check that each unique element appears at most twice in the final array. To avoid this, validate your solution with a variety of test cases, both small and large, to ensure correctness. Now, let's discuss some valuable insights for interviews. The two-pointer technique is a highly efficient and commonly used approach for problems like this one. It minimizes the need for extra data structures and is well-suited for in-place modifications. Additionally, interviewers often prefer solutions that modify the array in place because this demonstrates an understanding of space optimization. Discussing edge cases with the interviewer early on is another smart strategy. For example, you could ask about scenarios like an empty array, arrays with only duplicates, or arrays with all identical elements. Explaining trade-offs is also key. If you're comparing approaches like brute force versus an optimized solution, be clear about their differences in time and space complexity. Lastly, think aloud as you solve the problem. This not only helps clarify your reasoning but also gives the interviewer insight into your thought process. Now, let's explore related problems that share similar concepts or techniques. For example, LeetCode 26, which focuses on removing duplicates from a sorted array, or LeetCode 283, where you work on moving zeros within an array. Of course, LeetCode 80, which we're discussing here, and LeetCode 27, which involves removing a specific element, are also closely related. These problems often build on the same foundational ideas. As for alternative approaches, one option is the hash map approach. Here, you use a hash map to count occurrences of each element and then reconstruct the array, making sure each element appears at most twice. While this method is straightforward, it requires extra space, which makes it less efficient for space-constrained problems. A more optimal method is the two-pointer approach. By maintaining two pointers, one for iterating through the array and another for placing the result, you can modify the array in place. This runs in O(n) time and uses O(1) space, though it may take more effort to implement. Finally, there's the brute force approach, where you iterate through the array and count occurrences manually, creating a new array to store valid elements. While intuitive, it's inefficient due to its O(n)² complexity and additional space usage. Each of these approaches has trade-offs, so it's important to choose the right one based on the problem's requirements. Great work! To recap, we solved the problem using an efficient two-pointer approach, achieving O(n) time complexity. This problem highlights the importance of mastering in-place array modifications and adhering to constraints. Thanks for joining, and remember to like, share, and subscribe for more problem walkthroughs. Keep coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!